Dear students, today I would like to discuss about the structure of electrified interfaces. Structure of electrified interfaces. Actually, in previous classes we discussed about the electrode solution interface. Okay, this is your electrode, metal electrode, and this is the solution. You can see that almost all the important things are taking place at this portion, that is known as the interface of metal and solution. Okay, so today we will discuss what will be the structure of this electrified interfaces, and I already told you that how the charge is developing on electrode. That means here you can see the ions, whether it is sometimes it is Fe2 plus or Fe3 plus. Already we discussed that how the charge develops on the metal. So sometimes metal will be positively charged, and some other times it will be negatively charged. Okay, and again I told you that this interface, what is happens at the interface, that is the structure of electrified interface. To explain the structure of electrified interface, there are a lot of models. The important models related to the structure of explaining the structure of electrical interface is the important models are three. One is known as the Helmholtz-Perrin model, and the second model explaining the structure of electrified, it's an improved model. It is known as the Gouy Chapman model, and the third one is the mostly accepted model, that is the Stern model for explaining the electrified interfaces. Okay, so I will take one by one Helmholtz-Perrin model, Gouy Chapman model, and Stern model. So first I will take the Helmholtz-Perrin model. What is this model? Okay, you see all the model is explaining about the structure of electrified interfaces. But you see that each model has its own limitations, and I told you that finally the Stern model is somewhat acceptable, and that can be a very good model for explaining the electrified interfaces. Okay, so let me first discuss about the Helmholtz-Perrin model. And another name of this Helmholtz-Perrin model is parallel plate condenser model. Okay, so what do you mean by this parallel plate? You will see. Okay, so I told you that already told you about the electrode solution interface. Okay, suppose this is your electrode and in contact with the solution. Okay, so this is your metal electrode. So let me first mark the positive charge here. Okay, suppose the metal is positively charged. Okay, what will happen here? So this is the metal side, and this side is the solution side. This is the metal side, and this is the solution side. So what happens here? You see in the solution side, metal is positive means the solution side it will be negative. So what happens at the interface we are checking. Okay, So here it will be negative, here it will be negative, you see, negative. So these are the ions, that is why I am drawing like this, okay. So it's actually a rigid model. The Helmholtz-Perrin model is a rigid model. So what do you mean by a rigid model? Rigid model means you can see that the clear cut positive charge here in a line, and also the negative charge in a line. So that is just like, it is just like a capacitor, you see, just like a capacitor. That means one charge here and another charge here, okay. So that is why it is known as a very rigid model, Suppose you draw a potential graph, potential distance graph of this model. This is the potential side, and x is the distance from the electrode. Suppose you are considering an electrode and solution. This can be this axis, that is the y axis, you can consider as the electrode, and this part is the solution. That means x means it is the distance from the electrode, okay. So I told you that there is an interface, and Helmholtz-Perrin model proposed this type of an interface. That means suppose the array of positive charge you can see here, correspondingly there will be negative charge. So like that he explains. That is why it is known as a very rigid model, okay. So this is the metal layer, that means y axis, you see, y axis. So how the potential drop happens in this model, that is what I am explaining. I already told you that the negative charge is here. This is the correspondingly the one plane I am drawing here, like this, one plane. So this is a similar plane like this, okay. This is the array of negative charge. So this is your electrode and positively charged, and this is the negative charge in a rigid fashion, okay. So now you can draw the graph, okay, graph of the potential drop. So how the potential drop happens, okay, from metal to solution, okay. So you can see, you can draw, according to the model, you can draw a linear potential drop from metal to this particular layer, and after that it will be straight, okay. Somewhat maybe it is decreasing also, okay. Anyway, it is a linear type variation, okay. So this is known as a linear potential drop. It's a linear potential drop, okay. So this is the rigid model, that is why I am explaining like this. You can see from coming from metal to the this particular layer, and this particular layer is known as is known as OHP. What is this OHP? OHP is, the full form is outer Helmholtz layer. It is known as outer Helmholtz layer. Sorry, not layer, outer Helmholtz plane. That is why it is OHP. Okay. So this is known as the OHP. So from metal to OHP there will be a linear variation, and after that it will vary linearly. Okay. This is a very rigid model. So this particular model is known as the Helmholtz-Perrin model, and also you can call it as a parallel plate condenser model. Okay. So next you see the other model is coming, that is known as the Gouy Chapman model. So Gouy Chapman assumed that these ions are we cannot hold like this ion is here, because these ions are in solution. Maybe some ions are struck with here, but some other ions, most of the ions will be scattered. Okay, only some. So he is actually questioning the existence of outer Helmholtz-Plane, outer Helmholtz-Plane. Outer Helmholtz-Plane may be there, but it is very weak, he is telling. So he explained the model in a different way that I will tell you. That is known as the Gouy Chapman model. So Gouy Chapman model actually made the model more flexible. So last model, Helmholtz-Perrin model, was not a flexible model. It's a very rigid model. But in the case of Gouy Chapman, he made it free. That means somewhat flexible. Okay. So this model, particular Gouy Chapman model, is known as a flexible model for the electrified interfaces. So let us see what is the Gouy Chapman model. Okay. So the second one is Gouy Chapman model. Okay. Gouy Chapman model. Okay. So I told you that Gouy Chapman is actually freed the system. That means it is more flexible compared to the Helmholtz-Perrin model. That means your metal is here. Suppose it is positive charge. He can say that some ions, there may be some OHP layer, but it is not a rigid layer. It is a more flexible layer. That means the negative charge may be some negative charge may be here, in the OHP, and all other negative charge is simply diffusing like this. That means he explained that there will be an exponential reduction of potential starting from the metal. So we can draw his model in the form of a graph like this. Okay. So suppose this is your potential, and this is the x-axis means the distance. Distance from the metal. So this is the metal side, and this is the distance from the metal, and this is the solution side. So just like we have explained. So simply he explained the variation like this. It's not a rigid model. I already told you. Simply he draw a curve like this. That means you can see this is an exponential reduction of potential. That means exponential decrease you can see. So this particular model is known as the Gouy Chapman model. Okay. Then we can just see what is the Stern model. I told you that this is somewhat most acceptable model about the electrified interfaces. Okay. So let us see what is the Stern model. Stern model is actually a combination of Helmholtz-Perrin and Gouy Chapman. So I told you that Helmholtz-Perrin, what he did, Helmholtz-Perrin model is a very rigid model. Already I draw the graph. That is a very rigid model. You can see a linear variation to the outer Helmholtz layer, and after that also the variation is linear. But in Gouy Chapman model, what happens? So he explained that here it may be rigid, but here it is not rigid. That means the existence of OHP, that means outer Helmholtz plane, is questionable. Okay. Anyway, maybe he is not completely ruled out the possibility of OHP here, but he explains like this. That means an exponential reduction of potential. But what about the Stern model? Okay. So we will just see what is the Stern model. And Stern model is actually the I told you it is the combination. That means it's a combination of these two models, that is the Helmholtz-Perrin model and Gouy Chapman model. Okay. So here one more thing is there when we are explaining this Gouy Chapman model. Gouy Chapman model is very much effective, that means it is highly applicable in the case of very dilute solutions. That means he is actually not accounted the ion-ion interaction here. So when in the case of a strong electrolyte, there will be ion-ion interaction. So when the ion-ion interaction is there, the ions are not much free. So that is the actual limitation of Gouy Chapman model. So that is why this Stern model is coming with a combination of these two. Okay. So it is actually this model is not ruled out the possibility of OHP, and according to the distance, that means when the ions are very close, to the metal surface, definitely there will be OHP. That means the Stern model is telling. That means very close to the metal, there will be some the possibility of some rigid structure. That is the Helmholtz-Perrin model actually. That means maybe very close to the metal, there will be some ions like this. You can call it as the stuck ions. Some ions are stuck at the very near to the metal electrode. And after that what happens? After that you can see the variation. So that can be a diffused variation. That can be a variation like Gouy Chapman. That means there will be scattered ions. Like this. So there are two types of ions. One is a stuck ions and other one is scattered ions. That means the first layer is rigid, but after that it is not rigid, it is exponentially it is decreasing. So that is why I told you that this is the combination. Stern model is the this I am explaining the Stern model now. Stern model is the combination of this Helmholtz-Perrin and Gouy Chapman model. Okay. So now you see what is the combination? What do you mean by this combination? That means here he is not ruled out the existence of OHP. OHP may be there. OHP, that means the outer Helmholtz plane may be there, but it is very close to the metal. And after that the variation taking place. So how can you draw the curve for Stern model, potential distance curve? So this is the potential and this is your x. That means x is the distance from the metal. Okay, so this is your metal. This metal is anchored on the y axis. Okay, so this is the metal side and this is the solution side. So what happens here? According to the Stern model, first there will be some rigidity, some linear variation, and after that what happens? After that it will behave like our Gouy Chapman model. So some rigidity is there, and that means this is your well defined OHP. It is very close to the metal, and after that the variation will be just like the Gouy Chapman model. So that will give some very good idea about the electrified interfaces. Suppose you are considering an electrode solution interface like this, Suppose this is your electrode, this is your electrode. You can see that inside the electrode, suppose this is an electrode, inside the electrode there is a potential, and this potential is known as the inner potential, and also another potential is there on the surface of the electrode. This is known as the surface potential, and after that you can see some potential here, and this potential is known as the outer potential. So it is, you see, there are three types of potential are coming in the electrode. One is the inside the electrode, on the surface of the electrode, and outside the electrode. Okay, so actually these three models you can see, it's a somewhat complicated model, but I explained it in a very simple way. That means Helmholtz-Perrin model is a very rigid model that explains about a well-defined OHP layer, and after that also there are linear variations. So it's a very rigid model, just like a capacitor model. Okay, Gouy Chapman model made it completely free. So he is completely not rolled out the OHP, but still he is completely freed the ions. So Stern model found that we need not roll out OHP, because OHP may be there very near to the metal. That ions are some stuck ions. After that, some scattered ions will be there. So that also it is there. So that is why this graph is coming from metal to when the distance increases, it will vary very freely after the OHP. So that's about the electrified interface. Okay, so please read about all these things. I think it is in physical chemistry, Atkins book, and also you will get some internet articles related to the structure of electrified interfaces.